All right, let's jump right into this explainer. Imagine, just for a second, a creature that feels, well, almost alien. A predator that looked at the standard, four-limbed blueprint of life and just completely threw it out the window, right? Yet somehow it still managed to absolutely conquer the world. Today, we're unpacking a literal evolutionary masterpiece, the snake. Let's get into it.
So, you gotta wonder, how exactly does a creature with literally 0 arms and no legs thrive everywhere? I mean everywhere, from the pitch-black depths of the oceans all the way up to the towering 16,000-foot peaks of the Himalayas. Aside from the freezing ice of Antarctica, snakes have claimed basically every single continent on Earth. They are an absolute marvel of biological engineering, but to really grasp how they pulled off this global takeover, we actually have to rewind the clock a bit. Looking at the fossil record, snake-like creatures date way back, up to 167 million years ago. But the real plot twist happens around 113 million years ago. We've actually found fossil evidence, like the Tetrapodopus amplicus, which was a 4-legged ancestor. Yeah, snakes used to have legs. So what happened to them? Well, it boils down to a mutation in their Hox genes. Those are the genetic switches that control limb development, and a mutation essentially just flipped the switch to off. This massive genetic shift basically turned their entire body into one incredibly stretched-out thorax. When you look at a snake, you're literally looking at a highly modified, super long rib cage. Wild, right?
And because this body plan is essentially just a highly expandable tube, evolution could scale this blueprint to some absolutely shocking extremes. On the micro side, you've got the modern Barbados thread snake. This little guy is just 4.1 inches long. It could honestly curl up and take a nap on a quarter. But then, flip to the other extreme, you've got the extinct Titanoboa. This prehistoric giant stretched out to nearly 43 feet. To put that in perspective, that is the exact size of an entire school bus. Same basic design, totally different scale.
All right, moving on to Section 1, Anatomy of a Hunter, Engineered for Efficiency.
Let's peel back the scales for a second. The internal biology making this limbless lifestyle possible is honestly bizarre. Think about us humans. We've got paired organs sitting neatly side by side, but you can't exactly fit that arrangement into a long, skinny tube. So, a snake's organs are staggered, sitting one right behind the other. In fact, most snakes only even have one fully functional lung. And here is the craziest part. Their heart isn't anchored in place by a diaphragm like ours. It's mobile. It can actually slide around inside their chest cavity so it doesn't get completely crushed when they swallow a massive meal.
And beyond the crazy organ layout, their senses are just totally off the charts. The real game changer for their hunting is the Jacobson's organ. You know when a snake flicks that iconic forked tongue? It's not just smelling. It's literally tasting the air in stereo. Because the tongue is split, it can actually detect which side a scent is stronger on. It grabs those scent particles and pushes them right up into the Jacobson's organ, located in the roof of its mouth. It acts like a built-in GPS, letting them flawlessly track down their prey.
Okay, so once they actually track down that prey, they've got to eat the whole shebang in one go. Now, we need to debunk a huge myth right here. Snakes do not, I repeat, do not dislocate their jaws. That's a total misconception. What they actually have is this super clever double-hinged bone called the quadrate bone. Combine that with a super stretchy elastic ligament at their chin, and the two halves of their lower jaw can move totally independently. They just stretch out incredibly wide. That's the secret sauce for how they manage to swallow things way, way bigger than their own head.
But here's the catch. As a snake grows, its skin doesn't grow along with it, which brings us to ecdysis, basically the scientific term for shedding. Now, we humans shed microscopic skin cells all the time, right? But a snake sheds its entire outer layer of keratin in one giant piece. It is exactly like peeling off a tight sock inside out. And get this, snakes don't even have movable eyelids. They just have these transparent scales over their eyes called brills. And yeah, even those eye scales get peeled off and shed right along with the rest of the skin.
All right, Section 2, the art of movement, navigating without limbs. So how do all these biological hacks actually translate into moving around? Well, there isn't just one single way a snake slithers. They actually use 4 entirely different modes of movement depending on where they are. Lateral undulation, that's the classic S-shaped wave we instantly picture. But say they get wedged into a tight, narrow tunnel. Then they switch to concertina movement, basically bunching up and bracing the back of their body against the tunnel walls so they can push the front half forward. And if you've got a massive, heavy python trying to sneak up on a meal, it uses rectilinear movement. It just slowly creeps forward in a straight, dead silent line, dragging itself purely with its belly scales. But honestly, sidewinding takes the cake. It's truly exceptional. If a snake is stuck on slick mud flats or totally loose desert sand, those normal S-waves just aren't going to cut it. They just slip and slide everywhere. So instead, sidewinders literally lift and throw loops of their body forward, only touching the ground at specific static points so they don't slip. It's a brilliant mechanical hack. And the crazy part? This method uses less than a third of the calories a lizard would burn to run that exact same distance. It's just pure, ruthless efficiency.
Which leads us to Section 3, Venom and Survival, Nature's Chemical Weaponry. Whenever we hear the word venom, our brains immediately jump to self-defense, right? But from an evolutionary standpoint, venom is primarily an intensely specialized tool for taking down and digesting prey. And the delivery systems vary across the three main venomous families. Viperids, so think rattlesnakes here, they sport these massive hollow front fangs that are hinged. They literally snap forward like a biological switchblade. Then you have elapids, like cobras. They also rock hollow front fangs, but theirs are completely fixed in place. And finally, colubrids, like the infamous boomslang, have these grooved fangs tucked way, way in the back of their mouth. But no matter the family, these fangs are basically just incredibly sophisticated biological hypodermic needles. And what exactly are those needles injecting? Well, snake venom isn't just one simple poison. It's a wildly complex cocktail of modified saliva loaded with different types of toxins. You've got neurotoxins, which completely short-circuit the nervous system, hemotoxins, which go right after the circulatory system and destroy blood cells, and cytotoxins, which literally start melting down cellular tissue. The venom is basically a predigestant. It's doing the heavy lifting, breaking the prey down from the inside out before the snake has even swallowed it. And finally, Section 4, Snakes and Humanity, Fear, Reverence, and Medicine. Human history and serpents are just so deeply intertwined, from our oldest myths to very stark modern realities. 100,000. Think about that number for a second. That's the estimated number of people who die globally every single year from snake bites. This hits hardest in rural areas where folks just don't have quick access to medical care. The World Health Organization even classifies snakebite envenomation as a neglected tropical condition. So the danger? It's very real, and it's very present. But here is the absolute wildest paradox of the serpent. That exact same venom, the stuff that makes these animals so incredibly dangerous to us, is also a literal treasure trove for modern medicine. Today, scientists are taking those ridiculously complex proteins found in snake venom and using them to develop life-saving treatments. We're talking drugs for strokes, heart disease, and even compounds to control severe bleeding during surgeries. It's poetic, really. The very thing evolved to take a life is now being actively harnessed by us to save lives. So I want to leave you with this final thought. The next time you happen to cross paths with a snake out in the wild, what are you going to see? Obviously, it's pretty easy to just see a monster. But if you remember the mobile heart sliding around inside its chest, the completely independent double-hinged jaws, and the unbelievable calorie-saving efficiency of a creature totally dominating its environment without a single limb, well, I hope you also see it for what it truly is. An undeniable evolutionary masterpiece. Thanks for tuning into this explainer, guys. Keep questioning things and keep your curiosity alive.